Okay, good morning, everyone. So let's kind of recap what we did last class period. So we did go through the randomization exercise, both for the CRD and the RCBD. I hope that was helpful for you to understand the difference in the restriction when we have blocks as compared to when we do not have blocks, and how that plays a role when we're randomizing things. And also, hopefully, this can be something that you can apply to your own research as you're planning your studies for this upcoming growing season. I believe that at the beginning of the previous class, I did ask you to pull from GitHub and have the partial RCBD script already in your project. So we have that 04 RCBD, if I remember correctly. Let me pull my own folder here just to make sure. So yeah, the 04 RCBD. So it did ask you to pull the data and the code inside here that I shared on GitHub. And we're going to be using this for today's exercise. So if you can go ahead and open that 04 RCBDR project to launch that in our environments, and then we're going to get started with the programming side. Now, did I ask you to also move the data frame inside the data folder, or just the scripts last class? Can you check if you go like just the scripts? Okay, so if you can copy and paste the wheat NK bulk.csv into the data folder of this project, please go ahead and do that. So this data here, you can either find on your GitHub folder that you're pulling, or you can also find it on the so the 03 CRD has the same data. So if that's easier for you to get to, you can go to that and just copy the data from there. It's the same data set we're going to be using. So copy that data and paste it inside of the data folder of the 04 RCBD. Okay, while you're finishing doing that, I'm just gonna launch the partial script. So that would be, if I go under code here, it should be the 0208 RCBD partial on your side. And that's what we're going to be using today. Just open that up here as well. Okay. All right, so if you still need more time to move the data, let me know. I'm assuming you were able to move it to that folder. And I'm gonna start moving on here. So if you need more time, let me know. So today, our goal here is to create a very similar analytical workflow for a randomized complete block design. So there's going to be just a little bit of a difference here in the way that we analyze this. And because of that, I left you most of the code from the CRD, which is everything very similar to what we had already done. But so really the goal here is to reproduce that workflow, but now analyzing this data as if you were coming from a randomized complete block design. You can just go ahead and load all the packages for this class, but also for any other exercise that we do. If you run the chunk with the packages and gives you an error or gives you like a red symbol by one of the lines, you can just go one by one and loading them one by one to see where the error happens. And it may just be that you don't have that package installed, in which case you already know how to install packages using the install.packages function. You can just do that. Before we get into this exercise here, I do want to make a very, very important note here that even though we're going to be using the same data that we use for the CRD, this is just for teaching purposes, right? So this is just so you can connect the same ideas using the same data set. However, if this is your true actual data that you're collecting, you should only run the model that you plan that study with, right? So if you plan as a CRD, you should never come back and run as an RCBD because that's not what happened in the field. So just wanted to make that point. We are going to be recycling, I guess, this same data set to run CRD, RCBD, split plots, but you on your side would only run the model that you actually plan the study with and not be plugging and playing around with models like we're doing here. So this is just for teaching purposes. Okay, so first thing here, as always, or I guess second thing here is that we're going to read in that data set and save that into RCBD_df object. So it is a CSV file. So what function do we need here? Read CSV, right? So read_CSV. It could be the read.csv as well, even though there are some differences there. The read_CSV comes from is one of the packages within the tidyverse. So if you were able to load tidyverse, you can use the underscore. / to get outside the code folder. We go inside the data folder and then we read in the read nk bulk.csv. Just gonna import that. You should now see that in your environment as well. And we can just print it below so we can take a look at it. So it is the same data set. So it has 36 rows because we have 36 observations, and those are coming from 9 treatments that we have with different combinations of nitrogen and potassium rates, and then 4 blocks. I just left you the code there for the summary, as this is the same as before. So we're just taking a quick look at the summary here. Also using the glimpse function just to give us a glimpse of this by providing us with the variable class and also some initial values. Someone online had a question?
Yeah, can you scroll back up? I missed the data set we were putting in.
Yeah, so
Sorry about that.
this is the path. If you don't have this data in your data folder, you can just go back to the previous. So right now we're working on 04 RCBD. On the 03 CRD, that was the same data that we used for that exercise. So if you don't have this read nk bulk CSV in your data folder of the 04 RCBD project, you can just go back to the 03 CRD on your file system and copy that and paste inside of the data folder.
I was just making sure that was what you said. Appreciate you.
Yep. All right. Good deal. All right. So again, I left you most of the code here because this is not new to you. All of these steps we have already developed for the CRD script. So just a quick recap here on the wrangling. So we are transforming the rep, N rate, potassium rate to factors or categorical variable. This now becomes really important because our model is going to incorporate rep. So it's important to have rep as a factor. And a heads up here is that if you have your reps or blocks as numbers, 1, 2, 3, 4, as most people do, R is going to, by default, interpret it as numerical, double. You do not want that because if you do leave it as double, it's not going to be running the correct analysis. And we're going to see that in a second here when I show you the model. So always make sure to check that your variable names are, or your variable classes are what you would expect. And normally our treatment factors, even though they are rates in this case, they're numbers, but we really want them to be factors or categorical. Normally treatment factors are categorical. That's the most common type. So make sure that they are also transforming to factor by using that function factor. So we're doing that, and then we're just creating this column here, treatment name, that we're just combining the nitrogen rate, adding a plus, and the potassium rate into a string. So we can use this for plotting purposes in the end. So make sure you run this so we have this object in your environment. And then we can check here that now rep and rate and potassium rate are factors. That's what we wanted. Again, I'm just getting the summary just so we can see now that they're treated as factors as well. So we're not getting a statistical summary because they're not numerical. That's another way of checking for that. I left you all the EDA plots, the exploratory data analysis. I do want to stress that always do this. Always check your data with plots before you do analysis, after you do analysis. using plots is the best way for you to understand if there is something wrong, or even in this case, to create some understanding of what your treatments may be causing here. So we already talked about this. It doesn't seem like, at least based on this plot. So there is no statistical inference yet. We're just looking at plots without statistical data or statistical summaries applied to them. But this does not look like it has much of an effect of nitrogen rates. So when we look at the main effect of potassium, similarly, it doesn't seem like there's a lot of strength here on potassium rate. And when we look at that interaction using FASTA grid, it seems like here maybe there is something going on, right? So with the interaction, what you're looking for is that the levels of one of the variables, in this case, your nitrogen rate, are behaving differently as you compare across or within the levels of another variable which is on the facets, the potassium rate. So we see that the relationship between nitrogen rates is maybe different depending on the potassium rates. This is one of the ways that we can create the understanding of an interaction. So if we came here and everything was increasing, so from 0, 100 to 100 was always increasing the response, probably not an interaction between nitrogen and potassium, or perhaps if it was increasing, but to different extents. So maybe, maybe with the 0 potassium rate, it would be increasing a little bit, with the 30, a little bit more, and with the 60, a lot more. This magnitude of how much is increasing could also mean that there is an interaction. In our case here, it looks like the direction is different, right? Perhaps it doesn't have the same shape of nitrogen response within each one of the potassium rates. So maybe that's telling us that potentially there's an interaction here. We talked about the default contrast of set to 0 versus sum to 0. In R, the default is set to 0, and that is normally not what we want when we're running analysis of variance. So we're just changing that to sum to 0 by running this line of code here. And then, so make sure you do run that options. And then now let's start with our actual new coding, I guess, for this exercise, which is the model for the randomized complete block design. Let me take a look here at something, because I'm looking at my complete code and I'm just thinking if I want to show you something else. Oh no, this is not the correct code, the complete code on my side. This is what I want. Just a second here. No, I got the right one. Okay, so something that I'm sure you're gonna run into at some point in your research, and right now we're just gonna pin it, and I'm just gonna make a quick comment and move on, but we're gonna revisit this, is whether or not you treat your blocks as fixed or random. Right now, I'm gonna show you the model of how to treat your blocks as fixed effect. If you are not familiar with that term, don't worry, because after this exercise here, we're gonna have a lecture just on that. But for now, just know that we're running our blocks as fixed effects in this model. So we can come here, you can start coding with me now. We're gonna use this LM function, which is the same that we used for the CRD exercise. The data set, I just wanna bring here the data set again so we can print below. So it's the RCBD underscore DFW. I just wanna print this, oops, RCBD. CBD. There you go. Okay, so these are the columns we have. If you remember, the formula we used for the CRD was yield, kilograms per hectare, explained by, what we did was, I'm gonna just show you first the formula for the CRD, which we used last exercise. So that was N rate, asterisk, potassium rates. And then we give it a comma. We have to say what's the data set that this is coming from. So we say data equals to RCBD DFW. Okay. A quick reminder here. So we're using N rate, asterisk, potassium rate. Remember that that asterisk breaks down this into the main effects and interactions, right? So this would be equivalent to say N rate plus potassium rate plus N rate colon potassium rates, which is the full denomination of that. I'm just using a shorthand notation of asterisk here to make it simpler. So this is the model for the CRD that we ran. If we assume that this data is actually coming from an RCBD, what else do we need to change in this formula? If you remember from the effects model that we saw in the lecture and also the ANOVA table, what do we have to add here? The rep, right? So I'm going to add that first thing here. So I'm going to say rep plus and leave it like this. One thing to notice is that we are not allowing, or we're not adding to this model the interaction between rep and any of our treatment effects. And that is how it's supposed to be for a randomized complete block design. So rep is by itself, and then we have our treatment factors, main effects and interaction in the model. So you can go ahead and run this. And if we just run the summary, I do want to mention again that the summary for an ANOVA setup is normally not the most useful thing to look at because it's giving you a whole bunch of coefficients that whenever we ask for means, these coefficients are combined to give us the actual means of the treatments, but we rarely look at the coefficients themselves. This, however, it's important if you're running a regression, which is not our case. We're running ANOVA here. Okay, so we ran our model by the, and really a key point here is if you had this study planned and implemented as a randomized complete block design, and you come here and you run this model, you're running the model for a CRD, which may or may not have important consequences to your analysis. If your blocks were actually important because you did have heterogeneous experimental material, if you did not include rep here, you're actually gonna probably not have a very powerful model. You're not gonna be able to find treatment differences because the noise coming from the model is mixing your error and you cannot take it apart. If you did, however, ran as an RCBD and you run the proper model that includes rep, all the noise because of soil heterogeneity, for example, now is being pulled by the rep factor in your ANOVA. It's not being left in your error. And that gives you back the power of finding treatment differences. Okay, so if we just go ahead and run the proper model, let's check our ANOVA table. We talked about the type 1, 2, and 2 sum of squares. We do want to use the type 3, which comes through the uppercase A ANOVA function. I'm leaving that for you there. So now when we run this ANOVA table, we do have that rep as part of our ANOVA. We did not have it for the CRD, even though, and just want to make this very clear, even though in the CRD we had reps, right? We just did not control for them. We did not restrict randomization because of the reps, then rep does not appear in your model. In this case, RCBD, the reps were here because we constrained randomization by the blocks or reps, and that's why they appear here in the model. In this case here, we can see the rep has a p-value of 0.09 almost. So maybe there was something going on there that the rep was able to capture and remove that noise from the air, which then gives us more potential of finding differences. And then as we saw before with the CRD, we did not have an effect of the main effects of nitrogen and potassium rates. However, we did also see this effect of the interaction, right? And again, just as a reminder, every time you have interactions on an ANOVA table or in a model, when you look at the ANOVA table, you should start by them. And if they are significant, looking at the individual treatment factors here outside of that interaction would be misleading because there is an interaction. So we'll look at this ANOVA table and then we decide, okay, I have this interaction significant, so I should show the means breaking down by this interaction. A lot of times when I'm like, especially in conferences, I guess, when I'm watching a presentation and then somebody has like this complex treatment design, they have like three-way factors and a lot of things going on, and then they get into results and start showing me results, like it starts showing me plots or tables right away before showing me another table. I don't know what's even the I don't know if what the person is showing me is really relevant for that case, because it always should show a ANOVA table, so you inform your audience, these are the effects that I have in my model, these are the significant effects, and this is why I'm gonna show you the plots that come after, right? So your audience knows why you're showing them given plots. Okay, so I guess we talked a little bit about this, that the block effect was marginally significant. And that means that we did well by blocking in this case, because now we're decreasing the area of some of the squares by, remember that everything or anything that you do not explain through the other terms of your model is going to end up as variability in your error. So in this case, by doing an RCBD and by seeing the rep had somewhat of a significant effect here, we can say that this variability here, the sum of squares in the rep, if we did not have the rep here, if it was just a CRD, this would be falling in our residuals, which makes it more difficult to find treatment differences of your actual treatment factors. So here block was important to have in this case. Okay, so as you know, now we know what's significant in our ANOVA, but really before doing much more inference in this, using this model, we have to check residuals. So I left you here the code for that. So I left you the code. And just to recap here, the assumptions that we want to check are related to residual independence. So we do not want to see a pattern in that fitted by residual plot. Residual variance homogeneity, meaning that we do not want to see the spread of those points increasing as you increase the y-axis values. We want to see like a scatter of points. We want to find residual normality and also do outlier detection. So the first one here, residual independence, if you just go, I left you the code already, so you can just add or run that code. This is what it looks like. So I want to just take a brief moment here for you to think through this plot and just try to visually think of if there is or there is not a pattern. I'm going to give you 5 seconds to think about that. And I'm going to ask a couple of you to help me out here. And it's yours. What do you think? Is there a pattern or not?
It looks like it's the very least data in the beginning, and then it goes down, and again it's up, and it doesn't look like a specific pattern.
Yeah, that's right. Anyone else, or maybe someone that has a different opinion, that's valid as well. Vermont, what do you think?
The median BP is higher than the
So variability higher at the ends, a little bit less in the middle. So one thing that I always use is, because this is a subjective way of assessing, to help us get a little bit more objective, but still using a visual assessment, I like using the geom smooth, which I left for you. I just commented off on purpose. Right, so if we just uncomment that geom smooth and rerun it, this is what we see. So it seems like there is this movement, right? The rule that I use is, if the error bands are comprising the 0 on the y-axis, then I'm okay. It's not like a severe enough pattern for us to worry too much. So this is what that would be my personal interpretation of this plot, right? So perhaps there is a slight pattern, but it's not strong enough to make me doubt on the independence assumption, especially because this is a randomized experimental planned study that we did randomize. So remember, if you have a design study that you randomize, that's your entry into the assumption of independence. The problem is when you do not do a design study, so you go and collect data out in the world that is not being planned, it's just observational data, there could be all sorts of dependence going on in those models. that you're not even aware of. And so if this data was coming from an observational study, perhaps I would be a little bit more strict with my interpretation. But because this is a randomized study and I do not have reason to believe there is dependence because it was randomized, and this pattern here comprising the zero does not bother me. Yes.
Yes, one of the reasons that we consider this to be a null pattern will also be because it's centered towards zero. For example, if a big portion of that smooth line would have been on top or below that zero line, then it would have been chopped. Like,
Yeah, that's right. So yeah, let's say if this hump here would have been like higher and then come down a lot lower, and then we had a good portion of the fitted space here that would not be comprising the zero on the y-axis, then maybe that would be a stronger reason to believe that we had something going on. And then sometimes, I think we talked a little bit about this in a previous class, is that so if we do see a pattern here, it could be because we have dependence. So let's say if you were running an analysis of variance that had time as one of your factors. So let's say you sampled something over multiple times in the season, and it comes here, it would come here and you add that time, or let's say days after planting as one of your factors, and you see a pattern, maybe it's because time cannot be randomized. So it was not randomized, and because it wasn't randomized, there's likely some correlation or dependence between the levels of time. And because of that, we have to treat that differently. We're going to talk about repeated measures in the upcoming class where we address that. But it's not the case here, right? But so let's say so dependence because of maybe correlation in space or time can be something, especially if the data that you sampled the same plot multiple times over multiple in a frequency over time, but also perhaps in space. So let's say if you had depth, soil depth here in your sample, like 3 depths, and you come here and you add depth in your model, that could also be an issue because, as you may know, we cannot randomize space either. I cannot say that that the first sample that I pull out is 30 to 40, and then the first one is 0 to 30, right? There's not such a thing, cannot be randomized. So because of that, we have to treat that properly with repeated measure analysis. However, another thing that also may happen, maybe not as much in a NOVA setup, but more in a regression setup, is maybe the data that you have and the model that you're fitting are not a good fit. And we saw this example on the previous class where we had like a regression where the response was quadratic and we fit a linear, like intercept and slope regression, and our residuals look quadratic because there's actually a missing term in that model, right? So if we add the quadratic term to the model, then we did not see the pattern in the residuals. So it could be either of those things. In this case here, it was an experimental study. It was randomized. And because it is an ANOVA, we really don't have much space to play around with the model. So I would say I'm okay with the residuals looking the way they look. Same thing on the variance homoscedasticity. It does not seem like it's increasing as the x-axis values increase. So I would say is a homogeneous variance here across the space that we have. For normality, we were doing 2 plots. So the QQ plot was the first one. So we see now, and it's one thing that we're not seeing right here, but if you are curious, you could launch your 03 CRD and have them side by side and look at the residuals, because remember that residuals change depending on the model, right? And that's the reason why we check assumptions on residuals. So this model is slightly different from the CRD one because now we have RAP in the model. And that means that our residuals are looking different, right? So if you remember, the CRD did not have this pattern here. Also, this CRD analysis, I think the tails here were perhaps a little bit more off than the RCBD on this QQ plot. So remember, residuals will change. Your raw data may remain the same. Residuals will change as you use different models, as we're doing here in the same data set. Applying different models, we get different residuals. So residuals here, not, so this, in this case, just to remind you, we want to see most of these points on the black line. And most of them are, we have some slight deviations on the tails, but nothing that I would worry much about. Like something to worry would be like if you have really like something like, imagine an S shape going through a plot. That is a horrible deviation. You should not use the model as is if that's the case. In our case, I'm not too worried. Also on the density plot, it looks perhaps not almost centered around 0, not very much on the right spot on 0, but I'm not too worried about this either. And then lastly, for the outliers, so the outliers are really the only plot that of the ones we're looking at, the outliers detection is the only one that we truly benefit from normalizing our residuals, right? Because by normalizing them, we can have the 3 and -3 boundaries to make our judgment. If we do not normalize them, then the y-axis range of values will be dependent on the response variable. So it would be, like kilograms per hectare of yield, which would be a lot more than 3 and -3. So this is really the only plot that we truly benefit from standardizing our residuals. Okay, so let's extract the model means here. I don't think this has a lot of differences from the previous one, but I just left you here so I can remind you of that conversation we had around how do we extract means and how do we then make plots out of that, right? And make plots in a way that they're designed in a way to facilitate the message we're trying to convey and not to actually, make things more complicated or even confusing to our audience. So let's go ahead and come here. Let's use the means function to extract model means. The first thing we give here is the model name. That's RCBD_mod. And then we use the tilde to give what factors of this model we want to extract means for. So we did have the interaction significant, and that was the only significant term. And as we talked about, when we have interactions, we can break down that interaction in different ways. What I want to propose that we do for this script here is to do everything against everything else and use only that approach. So for that, we would just type the N rate _ kilograms per hectare, use the colon and give potassium rate _ kilograms per hectare. That's how we would specify the means for this interaction when we compare everything against everything else. So no structure in the way that we are extracting the means. If we print that, just give us the means, the standard error, the degrees of freedom, the lower and upper confidence limits on those means. So not on this script, but on the immediate upcoming script, I will ask you to take a look at this standard error and tell me what's going on. So I just want to, I guess make the point here to facilitate when I do ask you to come look for this. All right, so the next thing here is, I think I left you the code already. We're just getting the pairwise comparisons using the COD function. COD stands for compact ladder display. It's just the way of us extracting the means not extracting the means, to do the pairwise comparisons and assign letters. We're saying reverse equals true, adjust equals to none, and asking for letters instead of numbers. I do, so I mean, we can just run that and print it. Now we're gonna have the letters for the treatment means. And I do want to just make a parenthesis here. I want to ask for help of that COD function. And if we come under arguments, let's see, it's not. Yeah, I mean, the function itself, it's not really giving us much of information about the levels or about the different adjustments that we can do. Let me come back to that. So right here, we're using no adjustment. So this would be, if you read on papers, the Fisher's least significant difference, that's what no adjustment is. And then from that would be the, so really, you know, I think this is something interesting that is not, I think is not mentioned often enough. So we run the model, and the model is its own thing, right? And then we use the ANOVA function to check what was significant, and then use the ANOVA function results to decide how we're going to do pairwise comparisons and extract means and so on. Really, if you think about it, there's nothing stopping you from running your model, your LM function, and coming straight out to your means, and then CLD. There's nothing stopping you from there, right? There's not a pipe flow that you need to have the ANOVA somewhere. Having the ANOVA table, looking at the ANOVA table results and making a decision based on that, on what you're going to do after, is one way of safeguarding yourself, right? Because you're showing your ANOVA, seeing what's significant, and then deciding based on that on what to do. That is what is basically Fisher's least significant difference approach, is you're using the ANOVA as your filter to tell you how to look at your means and do pairwise comparisons. And then once you come here on extracting means and doing pairwise comparisons, now we have this option of adding different adjustments to make it even more strict. Of course, in this case here, we're making more strict by requiring that two treatments need to be even more different for me to say A and B. Perhaps if you use, we can do that test here. So if you use none, so this is applying no adjustments, and we just print that. We see the letters go through from A to E. One of the most common adjustments that people do use is the Tukey. So if you change the Tukey and you, interesting. It's giving me this notes. I don't remember seeing it. But if we just run it, now it's going through A's and B's, right? So we applied an adjustment that made it more difficult to find statistical differences. And this is just to control false positives in this part of your data. I guess I did not plan to talk too much about that, other than to say that the more comparisons that we do, the higher chance we have of finding false positives. So saying the two things are different when they're actually not. And using adjustments is just a way to overcome that, to make it more difficult to find differences using a given adjustment. I'm just going to leave it as none. I do want to ask you to leave as none, but for your own research, you can make that decision on your side and decide if you want to use Tukey. There's others like Duncan that thinks perhaps one of the most strict adjustments after Tukey. And there's a few others that you can use here to be even more strict. So if you are worried about false positives, as far as saying, you know, if two treatments, they need to be very different for you to say they're different. If that's what you want, then you should be using an adjustment. If you're not as worried about that, you just want to see differences within your treatments, you may just use no adjustment. And I see both in the literature, at least in the literature that I read and publish in. All right. I guess another parenthesis here that I think is worth mentioning. So if you plan ahead and you say, okay, I'm going to run this design, I'm going to collect this data, I'm going to run this without adjustment at a alpha level of 0.05, and you predetermine that and you stick to that, I don't think there's an issue. Where there is potential an issue is you're coming here, running no adjustment at 0.05, and not finding any difference, and then you decide, you know what, let me just change that 0.05. So there's an argument here called alpha that by default is 0.05, are 5% most commonly used in research. If you come here and you want to be more lenient, you want to allow more differences to show up, you can increase your alpha, so you're making it easier to find differences, right? So if you come and change alpha to 0.1, and now we run it, you're going to see more differences, I believe. Or maybe not. So let's see, when we had, so 0.1 is going from A. So A is being completely by itself. So the first treatment here is 0.60. It's completely alone. There's nothing like it because nothing else has A, and have all B's, and then some C, B, C, C, D, and then D's. when we had 0.05. So 0.05, we're being more strict with our comparisons. You had a lot of things that were similar on the top. So all these have A's, right? So there are a couple ways that you can be more strict or less strict with your analysis, your comparisons. One is to change the adjustment, one is to change the alpha. So if you think of it, the most liberal, I guess you can be here. So the most easygoing you can be with your comparisons is to have an alpha of 0.1 and no adjustment, right? So this is what we will get in that case. The most strict we could be is perhaps using an alpha of, I mean, most commonly 0.05 is used. I don't see many people using less than this, so I'm just going to keep to 0.05 and then using some sort of adjustment. So Tucky is not it's not the strongest one. There are others that we can use, but if we use this example here, you know, this would be the most strict that we could be. So now we see that all these treatments are the same because they all share an A, right? So I guess to wrap this up, what I'm trying to say is as long as you come with a plan and you stick with it, instead of coming here, see what you get, playing around with alpha, playing around with adjustment, that is what I do not recommend doing. But if you have something in mind, like I'm going to use no adjustment in alpha 0.05, you're good. You should not have issues publishing these results. But if you come here and then some plots or some analysis that you're showing plots in a paper have an alpha 0.1, others have an alpha 0.05, some have two keys, some have no adjustment, that raises red flags because it looks like you're fishing, like you're p-value fishing. You're trying to find differences where you can and just making that. So this is just a word of caution. Okay, so just to make sure on your side, you want to have no adjustment in alpha 0.05. That's what we are going to use to keep going. I think we have some slight wrangling at this stage. Yeah, so this, if we just run that RCBD COD all, this is not a data frame. As you can see, like, even though it seems like it has columns, but it has all this text below. So this is not a data frame. So the first thing for us to be able to plot this is transform into data frame. So let's go ahead and add a pipe, use the function as data frame. You run that and you print it. Now this is an actual data frame that we can use further down. The next thing I want to do here is we have already done this in the previous exercise, but I want to remind you is I want to create a new column. So I use the function mutate for that I want to call it letter. And I want to basically have this column be the same as group, but without the white spaces in those labels. So I want to call this, or I'm going to use a function called trim WS for trim white space and just give that dot group name inside of it. So we remove the white spaces of that column. And then lastly, we're going to create that treatment name column as well. So add a pipe, we need a mutate. The column name is TRT name for treatment name. We want to say that that's equal to, we need a paste 0 function to combine a few different pieces here. So the first one is we're gonna paste 0 is gonna be our nitrogen rates. And we do not need to put that in quotation marks because that's the actual column name. But then you give it a comma, we need quotation marks with a plus, give another comma, and then we call potassium rate. If you run that and you print it, we did some light wrangling here to get this going with our plots. Right, so we have our treatment name right there. Okay, so on the previous exercise, you know, we kind of ended things at the publication ready plot, even though we did not have time to fully do a publication ready plot. We just did something basic and we stopped there and we moved on. So we wouldn't spend too much time of the next class period going back to that CRD exercise. Today, because we do have some more time, I do want to show you what I would do to this plot to make this publication ready and make it very professional looking. And whenever I ask you to create professional looking plots, I mean something like this. It doesn't have to be exactly like mine. There's going to be a lot of things you can apply your own taste or design ideas to, but I want to show you what I would do to make this publication ready. All right, so as before that I mentioned to you, I normally like to show my raw data along with statistical summary, meaning that I want to show my box plots, raw data, with letter separation, statistical summary together in the same plots. So let's go and get started with ggplot here. I guess at this stage, the only thing I want to tell you, I don't want to give it a data set right here, but the only thing I want to say is, so whenever we specify the AES, it is actually under the argument mapping. We just we don't say mapping normally because we just always give data set AES. Because I'm not giving a data set, it is expecting for that first argument to be a data set. And because that's not the case, if I just give an AES out of the bat here, it's going to complain at me. So this comes back to the ordering of the arguments we talked about in the intro class. So because I'm not providing data set at this level, I'm just going straight into AES. I need to provide that argument name, which is mapping. So mapping equals to AES, and I just want to say that the fill is going to be equals to treatment name. So here's a quick difference. I don't know if you noticed already. Everything that you specify at the ggplot level here is going to be applied to every geome that comes after. If you want something that you only want to be applied to some geomes and not to others, you need to specify in the AES of that geome only, and not at the top level ggplot AES. So just to make this different, tell you this difference. In this case, we are basically saying that I want the fill of every geome that comes below to be according to treatment name column. All right, so add a plus. The first thing here is I want to add the raw data as a box plot. So we're going to use a geom underscore box plot. We need to say data equals to. So this is the raw data. That's the object we're looking for. The name of that is RCBD underscore DFW. I'm going to print this just to remind you. So this is the one that has 36 rows. So it's the raw data that went into the ln function, right? This is what I want to show as a box plot. Let's give it a comma, and we need to specify some AES here as well. So the x-axis, I want it to be treatment name. So x equals TRT name. The y-axis, I want it to be yield, as that is the variable that we are analyzing. So yield underscore kg hectare. If we run this, you should get something like this. One thing that I want to change at this point is I do want to see through them a little bit more, and they're completely solid. So to see through, we're talking about transparency. If I want to change the transparency of everything and not just of some of them, I get outside of AES, add a comma, and there's an argument called alpha. I want to set alpha to 0.8. So this makes them just a little bit more transparent. And at this point, I think this is okay. The next thing is I want to add the points that make up these box plots. If you remember, we can do that using geom point. I think geom point is not perhaps the most elegant way because they are just like the points get stacked into this vertical line right through the middle of the box plot. So I do want to use instead geom jitter to give him a little bit of a jitter and look, more fluid, I guess. So we add a plus at the end of that parentheses that close the box plot. And let's call geom jitter. We again have to specify the data because remember, we did not specify data at the ggplot level. So we do have to specify each one of the geomes. So data here is equal to the same as we used for box plots. So that's the RCBD underscore DFW. We're going to give it a comma. I'm going to break line a little just to see the code a little bit better. And let's call the AES function so we can say what goes on X, what goes on Y. So X is going to be the same as for the box plot. So X is going to be treatment name. Y is going to be yield in kilograms per hectare. If we do this, this is what we get. I do want to play a little bit around with these points. So So something interesting here is I was expecting for them to be colored according to treatment name as well.
To get feel, that's why. If you follow.
Oh, okay, I know why. So here's why. So the default shape here that jitter gives you, or that geom point gives you, is a point that has color but not fill. But there's a whole bunch of options, and there's an option, and this would be, I think that this specific shape is shape equals 1, the value 1. But there's a shape number that is 21, that's actually the point, but it has a fill and a color that we can change. So if you just come here and change shape to be equals to 21, outside of the AES, so remember, if we're changing something fixed to all the treatments or all the values, it is outside the AES. So if you change your shape to 21, that's gonna do the trick. It's just how R handles those two shapes. The shape 1 only has color, the shape 21 has color and fill. Okay, I also want to change a couple more things here about these points. I want to make them more transparent. So we're going to add a comma. Alpha equals to, I want it to be 0.6. So they're just a little bit less prominent than the box plots. They're a little bit more transparent than the box plots. And I also want to increase their size. So I want to say size equals to 3. So they look a little bit more like bubbly, perhaps. Okay, so this is basically us showing raw data. Somebody online had a question? Nope. All right. So the next thing we're showing here the raw data, right? So the next step then would be for us to show the letters. So we can come here and add a plus. I want to use geom underscore label for that. Again, we need to specify what data we're going to use here. So that's going to be data equals to, so we called it RCBD underscore CLD underscore selected. This is the one that you need. And just to remind you as well, this one has 9 rows. So notice how, as long as data sets have common X and Y axis, you can bring in different data sets with different number of rows, right? There's no problem in that. You just need to, oops, I think I'm missing an A here. You just need to make sure that they do have the X's that are common, but then they don't have to have the same number of rows. All right, I'm just breaking code a little bit. I want to call the AES function. So again, we have to specify what is X. So X equals the name. The same thing for Y. Y equals, in this case, notice something interesting here. So I'm going to print RCBD COD selected below. It does not have a yield underscore kilograms per hectare column. What do you think should go on the Y-axis? What column name do you think should go on the Y-axis in this case? What did you say? So the letters, if we put the letters on the Y-axis, I don't think it's going to work. The mean, right? So the E mean is the column that is coming all the way. So it is coming from the E means function that made its way into the COD function, and now we're going to use here. So because this is not called yield kilograms per hectare, we could do one of two things. We could either rename this column to be the same, or we can just perhaps more easily just come here and say Y equals E mean. Let's see, we can just go ahead and run this. Oh, we got an error. Oh yeah, I forgot to say what I want to be displayed as the label, right? So I ran that and it yelled me saying missing aesthetics label, right? So I forgot to say what was the label that I want to show. So I come back on the AES of geom label and we say label equals to, and the name of the column is letter that we created above, or that we use the trimmed white space. Okay, so we do have the letters there. I guess I want to change one thing about this is that I want to have the background of this label being white instead of taking the fill of the box plots. So I can come back to Zoom label, get outside of the ES function, and I want to say fill equals to white. That's gonna force all of them to be white in the fill. So that's how it's gonna look like. There's a few more things that I want to change here, that I want to walk us through. So the first one is, you know, the X's titles are not professional, right? You would not publish like that. So let's go ahead and change that. I want to add plus function or the plus sign, hit return, and call the function labs. We've been using this function a lot. So this function allows us to change y-axis. So the titles of y-axis, x-axis, legend, the title of the plot, the subtitle, the caption. So there's a whole bunch of things we can change in it. Right now, I just want to change the x-axis title. So we say x equals to, if we look here, if we just take a moment to think of what these are. So if I just say treatment, I don't think that's specific enough. I want to be very specific in this case. Remember, we're sending this to nature, so we want to be very, very sharp. So this is basically the nitrogen rate plus the potassium rate values, right? So that's what I want to say here. I want the x-axis to be N rate plus potassium rates, and then in parentheses, kilograms per hectare. Also, inside of the labs function, add a comma, and let's change the y-axis. So that y-axis is going to be yield in kilograms per hectare. So if we run this, I just want to, let me decrease my font size so you can see both the code and the plots. Okay, next thing I want to do here is I always invite you to think about your colors that you choose and to be inclusive of color blindness, or people that have different levels of color blindness. So let's add a plus and change the fill here to follow a color scheme that is colorblind safe. So it is a single function here, but I've noticed that sometimes people have some trouble to determine how should they specify this. So I want to take a little bit slowly this step and just ask, what type of function do we need? What's the first word of that function? Scale, right? So every time that we have something inside of the ES and you want to customize that, we need to find a scale function. So if you type scale underscore, it's going to be alpha. So let's say if there was a variable here that we were changing the transparency of the fill according to a variable. You know, one example that we can think about here. So let's say that we had like a covariate, like end of season soil nitrate, which in this case could be important. I could have that column in my data set and I could change the transparency of my box plots according to that variable. So that would be a way to think about how you would use scale alpha here. But in our case, what is the aesthetics that we are changing according to treatment name? Bill? Does anyone disagree with that? So the way that you would know is you will go to your AES and look what is it that you're changing the fill or changing the color in this case. That was set up all the way on the top here where we change. So sorry if I'm being confusing between using color and fill, but in this case, it is fill, right? So the color of those box plots are changing according to the fill, which is treatment name. So if I want to change that, I should come here and use a scale underscore fill function. If I was actually changing the color, then I would come and use scale underscore color, right? So that's how we would adapt that.
Dr. Bastos.
Yeah.
What about one of the varieties packages? Didn't there like a colorblind option in those?
Yeah, so the next thing here is for us to use the varieties, one of the varieties color schemes. So if we start typing, I think, so there is a Veritas package that provides us that. There's also some that are coming directly from ggplot2, right? So the Veritas B for bin data, C for continuous data, and D for discrete data. So in this case, we want to use the underscore D for discrete because the variable that's being colored by it is treatment name, and that is a discrete variable, right? If we were coloring by yield, for example, so let's say you know, you wanted to color by the mean yield and you had a column that has the mean yield, you would say Veritas underscore C for continuous. Okay, so if we go and run this, these are the box plots that we get. So they're looking a little bit differently here. I want to show you one more thing that maybe we have not talked about enough. And I just want to show you a subset, very small subset of the options we can choose, we can change with that. As you may remember, if I wanted to change a lot of different things about the way that the plot looks, I can change it to a different theme. So the default theme of ggplot is called theme gray. This is what we're seeing. So if I wanted to change completely to a different theme, you can just add a plus and type theme underscore something. You're going to see a whole bunch of options there. And even if you change that, so I just changed to classic, but I want to further refine what I'm seeing here. I would not do that refinement inside of the theme classic. I would actually have to call the function theme by itself, right? So I would say theme, and then here I can change so many different things about this plot that I'm going to show you a few of them. So for this exercise, I actually do not want you to use theme classic. I just want to remove that if you type that, or maybe just comment it off. But I do want to come on the theme, which is where we would change things kind of like by hand or pick the ones that we actually want to change. First thing I want to change here is we do not need this legend because the treatment names are actually on the x-axis. So this is redundant. I do not want that in my plots. If I want to remove the legend completely, we can come on the theme function, and it has an argument for legend.position. So this, you can play around with this, that let's say right now the position of the legend is right because it's on the right side. If I wanted this on top, I can just say top and it goes on top. It also takes the arguments bottom and left. You can play around with that if you wish. I'm not going to show you all of them. But you can also provide, there are two other things you can do here. So if I want to place this legend specifically inside the plots, I can give two coordinates inside this plots, which because it is two numbers, I need a C function, and they go from, I believe, 0 to 1, or maybe -1 to 1, I guess I don't remember now. But let's try, let's say if I wanted, I'm just going to give like a 0.9 and a 0.1 value. It's kind of moving that inside the plot now. So you can, one of these is X, the other one is Y, and you can just play around with that number. Whenever you're looking for this option, you can play around with this. So there's also this option, but if you want to remove completely the legend, which is what we want to do, we can just open and close quotation marks and say legend position equals to none. So that removes the legend for us. Okay, now another couple of things I want to do here before we wrap up this plot is I want to remove, let's see what I'm doing here. So on the y-axis, I want to remove all the grid lines that we're seeing. So all of these Y lines going horizontally on this plot, I want to remove them. So we come here on the theme, we can add a comma, and it has an argument called panel dot. And as you start typing, notice how many options you have here in case you are interested. But the one I want to change is panel grid dot major dot y. So that's the one I want to change. If I want to simply delete it, this is something more specific to ggplot, is when you are playing on the theme function and you want to change something like this, you're going to have to use an element function. So as you start typing, there's element blank, grub, line, rect for rectangle, render, and text. If I want to simply remove it, I'll just come here and say element blank. And that basically removes Oh, I guess in this case, it removed the major Y, so we left the minors here. Let's say I wanna, if I wanted to remove all the lines on the Y-axis, I would just say grid Y, and that would remove all of it. Oh, maybe not. Maybe this is not, let's see. Grid, oh, I guess we have to specify both. So we have to say grid major Y equals element blank, add a comma, and do a panel grid minor Y equals to element blank. Yeah, so that way we remove all the lines coming across. We still have the ones on the x-axis here. Okay, I have one more thing I wanted to show you. Yeah, I think that was actually it. So in this case here, I just made, you know, perhaps a little bit cleaner, just leaving the box plots. And now I'm gonna say I'm happy with this. If you wanted to keep customizing, you're welcome to play around. But as far as I'm concerned, this is good. So I want to save that, and I want to export this plot. So if I want to save this plot to file, we're going to use a function called ggsave. We've been using this a lot of times already. So we open and close quotation marks to give the path where we want to save it. .. / to get outside of code. We go inside of output, and I want to name this RCBD underscore means.png. If you just run this, it uses the default size of 7 by 7 inches. So if you go on your files, click on the R blue button to go home, go in the output folder and look for RCBD means. This is how it's going to look like because that's the default. Something that I do, that I used to do, I guess, more in the past is you can come here on ggsave, add a comma, and you can specifically give it the dimensions you want this plot. So if you make width equals to 8 inches and height equals to 5, and we run this, and you then go back again to your files, output, and open that file that you just created, this is how that's going to look like. Just want to give you the chance of looking at this. So this is the way that I've been doing this, as far as like, I never trust how the plot looks like below the chunk. I always export it, look into the file, because as you change the width and height of ggsave, the plot will look differently on file, right? So I always check on file. And then Anis, one of my graduate students, actually taught me this trick, that if you are on a Quarto file, you can specify either at the title of the chunk or as an option of the chunk by using the hashtag sign and the vertical bar. Here we have a whole bunch of options of the chunk that we can change where. Oh yeah, there we go. Thank you. So yeah, fig dot width, we can say here, so we're using 8, and then fig dot height. Nope. There you go. You can see that I don't use this much. And if you change these options here at the level of the chunk, and then you print this map below, it's actually going to show you how it would if you use these dimensions on ggsave. So you can do either, just want to let you know. But don't forget to do export using ggsave, right? Okay, somebody, if we have to save fingerprint plots, which function will we use to save them? Pretty, I'm not sure what you mean by fingerprint plots. Perhaps if you feel free to open a issue or GitHub issue in our class repo, and you can show me an example, maybe the code or maybe the output, and I can try to help you. And if others perhaps also may be able to help you as well. Okay, so this wraps up this exercise. We created this publication ready plot. Again, I showed you one example of a very small subset of options that you have with ggplots. If when you're doing your plots, I would highly recommend you to Google something like how to change X in ggplot. You're gonna find for sure help on the internet and you're gonna be able to customize the way that you want. But I just wanted to expose you to a few more options that I use a lot. All right, so make sure you save your script. Also make sure that you go on the Git pane and you want to stage, give a commit message. You can say like finish RCBD exercise and then push to your GitHub repo. Please go ahead and do that on your side. I'm not going to do that on my side yet, but do that on your side. Awesome. Thanks, Kriti. Yeah, once you publish that, once you create this issue, we can try to help. But just as everyone here is staging, committing, and pushing, just a quick word is that ggsave is gonna basically export the last plot that you created. Doesn't even have to be within this chunk. So even if I have in another chunk, I run another plot. So let me do that exercise just to show you how ggsave works. So if I rerun this chunk here, where I had we're talking residuals. If I rerun this chunk now in the history of this is my latest produced map. If I go back to the chunk where we just created that figure and I only run the ggsave, so I do not run the plot above, just the ggsave. And now I look on my RCBD means, it's going to be the latest plot that was created, not just the plot in that chunk. Meaning that for you to make sure that you want to export a given plot, you have to run it and then run the ggsave right after to make sure that it exports what you want. And I'm saying that, Kriti, because perhaps whatever is the code that you're using to create a plot, if you just add a ggsave after that, I think it would work. You know, I know for sure it would work if your plot is a ggplot object. If it's not ggplot, perhaps it would work. I'm not sure. Never tried. Okay, so we have here.
Hey, Dr. Bastos,
Yes.
I don't know why, but it hadn't had this till today. I went to go do a git push and my git tab is gone and I have no idea why.
Okay, so if your Git tab is gone, I know we've had that happen before with other students. The first thing I try is if I come under view, on the top here, the RStudio menu, if you
Yes,
go
sir.
under view and then you go on show other panes. Oh, maybe in my case actually is right there. It's like show Git.
I don't see that. I don't have that option.
You don't see it?
No, sir. Like I said, I've had last Thursday git was there, but I don't see it today. I don't know why.
So Pramod had a similar issue. Do you remember what was the? Oh yeah. Okay, so thanks, Pramod. So and this is perhaps a good word of advice for everyone. Are you using a Windows or Mac?
Windows.
Okay, so we've seen something like that or a similar issue with Windows users, that it seems that Windows has a limit on the number of characters that it allows you to do some things. And if the number of characters of the path is too long, it gives you issues. So Pramod here had that issue. I know Benita also had, I think Neva had, other students in the class also had an issue to some extent similar to that, where the fix was basically to decrease the length of the name of the folder or the script or both. So the total path is shorter. So what I mean by that is, you know, if you would go here on the code folder and you look at the length of your script, you can try to decrease that. So let's say if we're talking about the RCBD partial, if you rename that, it doesn't have to be through RStudio. It can be just on your regular renaming of files. You can rename this to something shorter. So maybe let's say like 0208, something like that. That may help. If that by itself does not help, I would say maybe rename the folder that you have for the course, because that is a long name in itself. So if, like in my case, it's a very long name, my folder, right? So if I just open that up, It's like 2024 CRS, you know, it's a very long name. So if you just rename that folder to be a shorter name as well, that may also help you to fix that issue.
Okay, yes, sir. All right, if I can't get it, I don't want to hold a class, but I
Yeah.
I don't
Try that. I think
I don't
that's gonna probably be the fix. And it's
I
not like
changed the name of the script and nothing happened. On one thing, I don't know why this is also doing it too, and that maybe this has something to do with it. I went through when I was naming all my files and creating the project, and it's instead of just going 04 underscore RCBD, it has dash and then the name of the class folder that I have personally set up under it. I did not select that.
Maybe
So I
let's
don't have,
connect by Zoom afterwards and I can take a
yes,
look.
sir, that's fine.
Yeah,
That'd be fine.
we connect after and troubleshoot that.
Yes, sir. Thank you.
Yeah. All right, so after you do all that, I think we're done with the RCBD with blocks fixed. I do have a lecture that it's kind of a short lecture. I think it would fit in the time here because we're going to 11:10 today. So I want to start that, and then next class we can be ready for the next exercise. All right, so if you come on my website, I have this new lecture available for today. So if you just click on that link, you can open that up. It's going to be fixed versus random effects. That's what we're going to be talking about today. Okay, so before we get started here, I just want to have an understanding at least of the people here in Athens that I can see in one glance. Who here knows what this is and what the differences are, and you're familiar with it? So if you're familiar with the concept of fixed or random effect, raise your hand, please. Okay, so nobody raised a hand. So, okay. So we're gonna go through this perhaps a little bit more slowly than I was planning, but that's fine. If I'm sure it's still gonna be confusing at the end of this lecture, because this lecture is not made for you to be a pro in fixed and random effects, but I think it's gonna help as we do the next exercise for you to understand a little bit more what we mean by this. Okay, so fixed versus random effects. This is very important especially when we're doing experimental design types of analysis, because it tells your audience how the variables in your model are contributing to your model itself. And I know right now that's very vague, but I want to create this understanding here as we move along. Okay, so today, or in this lecture, we want to explore the concept of fixed effects and fixed models, random effects and random models, and also mixed effect models. So we're going to talk about those concepts, what they are, some examples, and so on. All right, so starting off with fixed effects. This is the most common thing that you're going to use. Normally, your models are going to have at least a fixed effect part of it. So everything that we worked until now were fixed effect models because they only had fixed effect terms in them. Normally, what is a fixed effect and what makes it fixed? Normally it would be factors with systematic levels, in the sense that if you go back to our example of nitrogen and potassium rates, that we deliberately chose given rates, right? It's not like I had this population of rates and I randomly selected 3. It's like I chose 0, 100 to 100, whatever that was. We chose those levels. Whenever you choose the levels of something because you're interested in those specific levels, that is telling you that this is a fixed effect. You want to know the effect of that specific level on your response variable, in our case, yield. And because of that, because you choose them deliberately, you're not sampling them from a population, then you can only make inference on those specific levels, right? So I would say if I have a 0, 100, 200, and I do analysis of variance, I can say what my yield was at 0, 100, and 200, but I cannot really say what happened outside of that or maybe in between those levels. Also, because you are deliberately choosing those levels, you can replicate another study with the same levels, right? So I can do the same study in 3 different sites or maybe different years and have the exact same levels selected. So the same nitrogen rates, potassium rates, and so on. And whenever we treat our terms as fixed effect level or fixed effects, that's because we're interested in their effect on the mean of our response variable. So I want to know, what is the mean yield when I apply 0 kilograms of nitrogen per hectare? The mean is the main part here. So fixed effects, I want you to, when you think of fixed effects, I want you to think that the measure of interest from that is the mean response on our response variable. So everything we've been doing up until now are fixed effects. So if you think about it, our rates of potassium and nitrogen and their effect on yield, they were treated as fixed effects in the model. That's what we've seen until now. So if you have a model that only has fixed effect terms, so our CRD model we ran, our RCBD model that we just ran, those only had fixed effect terms in the model. When that's the case, the model is called a fixed effect model, right? Because it only has fixed effect terms in it. Also, because of that, so every single model that we run have at least one error of variation or source of error. And in our case, if you're using a fixed effect model, that source of variation or error is our EIJK that we had in the end that we used to estimate the sigma square E, right? So if you remember, sigma square E is our mean square of the error, which is what we use to test the treatment effects on that ANOVA. If we have a fixed effect model, the only source of variation or error in this model is going to that error term, which is the sigma square of the error that we use to test treatment effects. In R, we run these types of models using the function LM. So the function LM, which is what we've been using until now, only handles one error source, which again is that leftover error residual for the model. If you, just so I have some idea here, who here has been using SAS for similar types of analysis? Okay, so no one. So I'm not going to really give SAS examples. All right. So just to remind you here, I'm just bringing a model for us to look at. So Yij is the observation that we're making. So let's say yield. So yield observation that we made, explained by an overall mean. Our alpha I here, I'm just simplifying the model that we have on our motivation example, just to not complicate things. So here I'm just have the overall mean, and then alpha I is the differential effect of the ith nitrogen rate. And then we have our error Eij. So Eij is our only source of error in this case, or of random error. Everything else is being explained by the model. What is not explained by the model goes into Eij. So the only source of error or random variability in this model is Eij. And if you recall, Eij, again, is the residuals of this model. And the way that we check the assumptions is assuming that is identically independently distributed normal with the mean of 0 and a sigma square of E. This is going to be key for you to remember, because now with random and mixed effect models, we're going to start having more sigma squares. And I just want to remind you that the sigma square associated to the residual error is sigma square E. And again, in fixed effect models, this is the only source of random variation, is Eij, is the error of that model. Okay, so what about random effects? What is that? What does that mean? And what are the differences here? So random effects would be factors with non-systematic levels. You can think about this. What I mean by this is if you have a population of something. So let's say I have a population of nitrogen rate treatments that range from 0 to 300. And I'm not interested in any particular level. I just want to know, I just want to pick some random numbers from that population of rates to give you an idea of the variability of that population. So if that's what I'm interested, which normally is not what, at least not in this example here, But if that would be what I was interested, I would basically sample 3 rates within the sampling space, let's say from 0 to 300, sample 3 random levels of nitrogen and use them as a random effect in my model. Because again, I am not interested in the mean effect of those rates on yield. I'm interested on the variability of those effects on yield. So when you think of it, interested on the variability of those effects on yield, we're thinking about random effects. And because we do sample levels kind of randomly within the population, we can make inference to the whole population. So I could say, so let's say I pick 3 random rates, and then I run my ANOVA, and then I get this effect on the mean yield. And then I can say that the mean yield of that population of rates would be that mean that I'm getting across all these levels, but not to any particular level. I'm not interested on how 0, 100 to 100 impact, but how the population or the sample of levels within this population are impacting the mean yield. So I would not have a mean for each treatment. I would just have one overall mean that I have a distribution of variability around it that is coming from the random effects. In this case, nitrogen rates of 3 different levels that were randomly selected from this population. And because we are randomly selecting these levels, you may not be able to recreate the same study across other situations. And a key difference here is that whenever we treat something as random effects is because we're interested in the variance of that effect, not the mean. I don't care about the mean effect of 0, 100 to 100. I want to know what's the variance effect that has on yield instead. So some examples here of things that normally people treat as random in studies: years, sites, and blocks. So let's just stop for a moment here and talk about perhaps years and sites. Let's say that your goal is to create a model where you predict, or not predict, but where you explain something, let's say nitrogen response in corn or cotton or whatever, across Georgia. And you're gonna have to choose some sites and some years to run your trials, but you can kind of think of those sites and years as a random sample of all the potential sites you could run your trials. So you're not necessarily interested to say that here in Watkinsville, the response was X, and in Midville was Y, and in Tifton was Z. You want to know what's the variability of the response across the state. So in the end, you can give a statewide recommendation and not just say Watkinsville is X, Midville is Y, Tifton is Z. So in that case would be one example where people would treat years and sites as random. So they don't want to give a specific recommendation to a site or year, but they want to sample from this population of potential years and sites within Georgia to create variability and then understand that variability effect on the average yield across Georgia. So that's kind of, I think this can be very abstract, but, if you're not fully clicking yet, I hope that when you do the exercise, it's going to help you a little bit more. But that's kind of the concept is if you're interested in the variability overall, and you're not interested in saying a response specific to this level, but to a population of potential levels, you would treat that factor as random. I do bring blocks here as an example because at least when I was going through grad school, I think I had classes that were teaching me this a little bit differently, or maybe we're not talking through this. And I kind of got this idea that I should always treat blocks as random. And then I ran into another different type of literature that actually, was proving that depending on the situation, it may not matter. And you may actually be better off treating blocks as fixed. So maybe blocks is going to be the case where if you're running RCBDs, that's going to be the case that you're going to have to stop and think, should I treat these as random or as fixed, and why?
I have a question.
Yeah.
So, like for example, I have one trial in Athens and one in Tifton. So, and I have a mixture of different samples, like some samples are from colder regions, some samples are from hot regions. And I want to test at a specific site, like how they perform when it comes to the yield. So, aren't those mixture of samples the random, and these years or sites, these can be fixed.
So one way that I think can help us think through this is so the model that when we specify the model is going to be, you're still going to have to call out those columns in your model, right? So I guess in your example, because I mean, right now you're seeing samples, and I don't think a model would have a term that would be called sample, right? Because you need to have variability. So let's say our sample would be our plot, right? But we need the rep to create variability to be able to estimate the variance that then is used to test treatment effects and do pairwise comparisons and so on. So we would normally not have sample as a term in our model, because if you go to the level of the sample, then you don't have replicate, right? If you go to the level of the treatment, then you have replicate of that treatment, right? So I'm telling you that because maybe to think through what you're saying is we should understand that what is the structure behind the samples in a way that you would have to have a column in your data that goes into the model, right? And samples will not be that column. So maybe if we think through your example.
Make it as genotypes. Like
Okay.
genotypes.
Okay, so if you're different samples or different genotypes, and then your question, what is your objective?
So I want to keep my genotypes as random because they are random. They are from different regions, and I want to test them in a hotter region, how they perform.
Mm-hmm.
So sites can be fixed, right?
Yeah.
We cannot change sites. So in other words, it depends on our objective of our experiment, right?
So let's say if you have a model where you have sites and genotypes, right? And you really don't care about the mean response, and this is a great example. So let me just perhaps explain a little bit more. So if you have a variety trial that you run across many sites, right, in many years, and you have a column that is genotype, you have a column that is site, maybe one that's year, and you're not interested in the mean of the genotypes, you just want to explore the variability that all those genotypes bring to the table, then you can treat genotype as random and have site as fixed. And then basically it's going to give you a site average response, but it's not just an arithmetic average. It's going to be the average coming from, or the mean coming from the model, which takes into account the actual random effect variability coming from genotype. Right, so I guess the mean is actually not going to change much if you have balanced data, but the error around that mean is going to change. And we're going to see that why in a little bit here. Yeah, but that's a good example. And I think a lot of this, so if you're not in plain breeding, I think maybe how you treat ears, sites, and blocks is the most common topic you're going to get when it comes to treating something as random or fixed. But in plain breeding, there's a lot of other conversations about, you know, especially when you're trying to dissect the genotype by environment interaction, what do you treat as random? What do you treat as fixed is going to be important. And that was a great example. Thanks, Joseph. Okay, so a random effect model then. So if I call a model random effect is because it only has random effects. So it has no fixed effect in it. And it does need to have more than one source of variation or error, because now it does have that sigma square E for the error, but it needs to have at least another sigma square coming from the random effect in that model. And in R, we do not use LM for that. LM does not handle random or mixed effect models. So for that, we're going to use, I mean, there's different functions and packages we can use. I'm going to show you how to use function LMER from package LME4 that can truly handle multiple different errors in our analysis. So another example here of a random effect model, the model itself, the way it looks, it's not different from before. It's more on how those terms are explained. So still you have Yij, still you're observed from a given rep in a given nitrogen rate. If you have a random model, your overall mean is your only fixed term that you get from this model. So if you're looking for means, you have only one mean. That is your overall mean right there. In this case here, I'm treating alpha I as the random effect of the ith nitrogen rate. So let's say if I had randomly sampled 3 nitrogen rates from a population that goes from 0 to 300, and treated that as random in my model as well, that variability around nitrogen rates, not the mean of the nitrogen rates, but the variability around them is going to be expressed within alpha I. And we still have the residual EIJ. Now there is a difference. If you have a random or mixed effect model, which we're going to talk soon here, you're going to have more than one source of error. So you're going to have, in this case, your alpha I, because this is a random, alpha is a random effect of the nitrogen rate. That variability around those nitrogen rates are going to also be IIDN with a mean of 0 and a sigma square of alpha. So notice that this term has its own error term now. Before it did not have, we only had means. And we still remain with our error residual that also is, we're also assuming a distribution, a random distribution of that with a mean 0. So the mean is the same, but the variability around that mean is different. So for the error is sigma square E. For this case, alpha I, which is related to nitrogen, is sigma square alpha. So they have different errors. So now we're taking the error that before was just in the error term, the IAJK, we're partitioning that between the error and the actual random effects that in this case are related to nitrogen rates. Because of that, now for the variance of any response variable that we have is going to be partitioned. So now we have the total variance of a given response variable is going to be explained both by the variance coming from the effect of nitrogen and the variance coming from the error, the residual error as well. Whereas before we only had the residual error when we had fixed effect models. So we can kind of think about this, the sigma square A, so the random effect is your group variance. So it's going to be attributed to variability between nitrogen rates. Whereas your sigma square E is that residual variance that is attributed to variability within the nitrogen rates. So basically how much variability we're explaining between our nitrogen rates, and whatever is not explained here goes to our error variability. I just want to make a quick comment here that we have 3 methods to estimate various components. So the one that we've been seeing up until now is just ANOVA type 3 sum of the squares, which is also called methods of moments. I don't really need you to know much about what's going on behind the scenes or much more details about this, other than to say that there are 3 and a few of their characteristics. So this one, the first one, is based on mean squares, as we've seen already. And an issue with it is that it can yield negative estimates of variance, which, there should not be a negative estimate of variance. That is not a thing that happens in nature. So this is the issue with this approach. Another approach is maximum likelihood, that basically maximizes the likelihood function. And it is known to underestimate the variance components. So it is biased. The last one, that is actually what we plan to use most of the time, is restricted maximum likelihood, or RML for short, that maximizes the residual likelihood function after removing the fixed effects from the model. And it produces unbiased estimates of variance components. So that's what we would like to use. And it is especially the preferred method if you have unbalanced data. So just keep that in mind, that if you have unbalanced data, let's say you lost a plot, maybe you lost a whole rep, and you're treating your blocks as random, you should use RML as your method of estimating the variance components. You know what? I thought I was going to get through this faster. I don't want to rush because it is a really important topic. So I think this is a good stopping point for today. Next class, we can pick up from here, finish this lecture, and then get into an exercise where we're going to treat blocks as random. And then I want you to see the differences of what's going on and what are the consequences of treating a block as fixed or random, so you can make an informed decision on your studies when it comes to that. So let's stop here. Let me take your attendance. All right, go ahead and claim your attendance. And then on Thursday, we're going to continue this exercise. I have already pushed to GitHub this morning the script that we're going to be using on Thursday. So if you want to go ahead and bring that, make a git pull, move that or copy that script into the code folder of this current project. So you don't have to create a new project, you can just use the same one. Just make sure you bring in the partial script so we can get going next Thursday. All right, that's what I had. Any questions? All right, I don't hear anything, so I'll see you all on Thursday.
I'll send you a Zoom link in a little bit if you're still good to meet, Dr. Bastos.
Sounds good, sounds good.
Can you give me a little bit, maybe can I send it at 11:30 if that's good with you?
Yeah, that should be fine.
Thanks.
Thanks. Bye.